Hello everybody. So, in the last class we have been discussing about the star and the delta circuits. We continue our discussion with these three phase circuits, now with special emphasis on unbalanced loads. Till now we have been seeing all the loads were of the equal value, equal magnitude, but we should also know what happens if the three phase loads, that is the loads in each phase are different, which is what would happen in most of practical cases. In the case of the star, we said that if we have a source, three phase source like this, this is a three phase source, it has a central point neutral, that is star connected source, and let us say you also have a load which is in star, let us say this is A, B and C, and this is also A, B and C, and there is a neutral point N. We connect the A to A of the source, B to B source and load, and C to C source and load. This is EAN, EBN, ECN. Now, if the loads were not equal but unbalanced, that is R1, R2, R3, that is R1 is not equal to R2 is not equal to R3. Under such conditions, we saw that the currents through each of the phase loads are going to have different effective values, and as a result, what was supposed to be IA plus IB plus IC is equal to 0 instantaneously in a wire that goes out from here is not 0. So, if we make a connection, between the neutral of the source and the neutral of the load, then IA plus IB plus IC instantaneous values will flow through this, and that will have an RMS effective value, and this value will not be equal to 0. When such a connection is made, then the EAN and its single phase load becomes a independent circuit, EBN along with its the EBN circuit is EBN along with its circuit is one another independent circuit, and ECN along with its circuit, along this becomes another circuit. So, we have these three independent circuits, and the voltages across each phase is EAN, EBN, ECN, which is as decided by the source. So, there will not be any anomalous behavior or any voltages due to the unbalanced load. The voltages across all the three phases will still be the same as decided by the load, whereas if this green line, the neutrals are not connected, then the unbalanced currents will flow through, will get mixed up and flow through the other loads, and then you can have voltage distortions. So, in a star, to take care of the unbalanced load, you would normally connect the neutral points. Now, in the case of the delta, what would happen, because there is no concept of a neutral. So, let us take an example and try to work out what could happen in the case of a delta circuit. Now, let us say we have the following delta circuit, that is, I have a capacitance, I have an inductance, and I have the resistance R, L, C, all three. Each phase is having totally different types of impedances. Let us say this is the A phase, A point, B point, and the C point, and we have the three source terminals A, B, C 120 degrees apart from each other. They are connected as indicated here, and we have the B, which is connected to the B terminal of the load, and we have the C, which is connected to the C terminal of the load. So, these are the three delta point terminals. You have X C, X L, and R. Each phase is having totally different type of impedance, and the impedance values are not same, and therefore, the load is an unbalanced load. So, under these conditions, what is expected to happen? Let me push it a bit. Okay. Now, we have the voltage across R, which is the line voltage or the phase voltage, because in the delta circuit line and phase voltage are same, which is EAB. The voltage across L, EBC, and the voltage across the capacitance is ECA. See, that is the sequence. Now, based on this sequence, we have the vector diagram. Let us say we have the EAB, ECA, we have ECA, and we have EBC, all 120 degrees apart. So, BC is lagging EAB by 120 degrees, and ECA is lagging BC by 120 and AB by 240 degrees. Okay. This we know. And there are three line currents. This is IA, IB, and IC, and of course, three phase currents IAB, this is IBC, B to C, and then ICA, C to A. So, this is cyclic in nature, A to B, B to C, C to A. Now, if we take IAB and EAB, the load here is a resistor, and therefore, we expect IAB to be in phase with EAB, what is applied across the resistor. Therefore, we shall put IAB in phase. Now, I will take the effective value IAB phasor is in phase with EAB phasor. These I is what I am showing the instantaneous values, but what I am going to plot here are the effective values, because it is a phasor diagram. Now, if you take BC, the voltage BC here, and the load there in the BC arm is an inductor, gives you an inductive reactance XL. So, what should be the nature of the current in terms of phase angle? We should see that the current IBC should lag the voltage across the inductor by 90 degrees, because it is a pure inductor. So, what do? We take EBC, and with respect to EBC, the current will lag by 90 degrees. So, IBC is going to lag by 90 degrees. So, if this is 90 degrees, this would be 30 degrees. 90 plus 30 is 120 degrees. So, IBC is lagging EBC by 90 degrees because of the inductive load. Now, coming to the capacitive, what is the nature of the capacitance? The current through the capacitive load, pure capacitive load, will be such that it will lead the voltage across the capacitance by 90 degrees. So, ECA, then it has, the current has to lead ECA, and therefore, we shall draw a phasor which is 90 degrees to this ECA, and that will be ICA. So, if it is 90 degrees to that, it will be 30 degrees from here. So, if I extend the EAB line down, so you will have a 30 and a 30 here. Okay. So, this is how the phase currents and the line voltages would look like, the phasor diagram of such an unbalanced system. Now, let us see what is the equivalent values of the currents which are along the 3 voltage axis. That is, if we project this current ICA onto this axis and all the other 2 axes, then we know the equivalent 3 phase currents which are flowing along the 3 axes. Okay. So, let us find out the currents along the EAB axis, along EBC axis, and along ECA axis. So, if we take along the EAB axis, you will see that along this axis there is an IAB term, then there is a projection, there would be a projection of ICA onto this axis, a projection of IBC onto this axis. Now, all these 3 together are going to form the equivalent current along this axis. So, that would be IAB, now that is in the positive direction. Now, ICA cos 30 and IBC cos 30 are in the negative direction, minus ICA cos 30 degrees minus IBC cos 30 degrees, which are the projections on this axis. So, that would be the value of the current along the EAB axis. Now, let us see along the EBC axis. Now, if you take the EBC axis, IBC, this current here IBC is 90 degrees with respect to EBC because of the inductive load. So, there is no projection of IBC on the EBC axis. Okay. So, we have only the projection of IAB on the EBC axis, that is negative IAB. Now, this angle here, now if this is 120 degrees, this is right through in between across. So, therefore, this has to be 60 degrees. So, IAB cos 60, there is a projection on this axis, and then ICA cos 30, there is a projection on this axis. IBC has no contribution because it is orthogonal to the EBC axis. So, therefore, if you take the EBC axis, along EBC axis the currents are minus IAB cos 60, that is that. Then we have ICA projected on the positive direction, which is plus ICA cos 30 on the EBC axis. Now, we take the third axis along the ECA axis. What are the projections? So, this if I project it, again we have a 60 degree because this is right through and this is 120 degrees between AB and BC. Now, there is a projection of IAB cos 60 on the ECA axis. Now, ICA is exactly 90 degrees from the ECA axis, and therefore, there is no projection of ICA on ECA axis. Now, IBC has a projection on ECA axis, which is IBC cos 30. So, we have IAB cos 60, which is on the negative part of the axis. So, we say it is minus IAB cos 60 plus IBC cos 30, IBC cos 30 degrees. So, these are the projections of the various currents on all three axes. So, equivalently we can say that these currents are all currents which are in phase with the EAB, BBC and ECA axis, like resistive loads, equivalent resistive loads put along these lines. So, let us just take this, copy, go to the next page, let me paste this. So, let us say that if we want to make it balanced, we want to make this load balanced, which means it should look like I should have a current along this, current along this, current along this, all equal amplitudes. Then we have equivalent of something like a resistive load and all having the same effective values, which means the whole system would be balanced. So, for that the equivalent current along the AB axis, that is this, equivalent current along the BC axis, that is this, equivalent current along the CA axis, they all should be of equal value. So, let us equate these two and then this with this. So, let us see what happens. Now, let us equate these two. Now, this of course is equal to I A B minus root 3 by 2 I C A minus root 3 by 2 I B C, and this is equal to minus I A B by 2 plus root 3 by 2 I C A, and this is equal to minus I A B by 2 plus root 3 by 2 I B C. So, you have equation 1, 2 and 3. So, let us first equate 2 equals 3. So, let us equate 2 and 3. So, this means we have minus I A B by 2 plus root 3 by 2 I C A should be equal to minus I A B by 2 plus root 3 by 2 I B C. So, here we remove this, So, we have a result which is I C A should be equal to I B C, and we will say that is equal to some value I. This is number 4. Now, let us substitute I for I B C and I C A in 1 and then solve for I A B. So, now we have I A B minus root 3 by 2 I C A minus root 3 by 2 I B C is equal to any one of these two currents, because we have already equated these two, any one of these. So, let us say it is equal to the 2 minus I A B by 2 plus root 3 by 2 I C A. So, we know that I C A equals I B C equal to I. So, we make that change, I A B, I C A and I B C is equal to the same value, and that is I. So, we have substituted I in the equation. So, now 3 by 2 I A B, taking I A B onto the left hand side, taking these onto the right hand side, you have 3 times root 3 by 2 into I. So, this leads to the following nice relation, I A B is equal to root 3 I, or I should be equal to I A B by root 3, should be equal to I A B by root 3. This is a nice relationship. Now, using this, what can we gain? If we go back here, let us try to find the values, what should be the values of the capacitance, reactance and the inductive reactance. Copy, paste, so what we have right now said that in this we have an effective value, we have effective values here, which after having been solved, the values are like this. So, here I is flowing, here also we are having I, and here we are having IAB, which is root 3 times I. So, we have root 3 times I. This is IAB. So, now we can find out what should be the reactance which will give this kind of a solution. Now, the effective values EAB is equal to EBC is equal to ECA is equal to E line or a balanced source which is applied, and therefore, XL is E line is the voltage across the inductor divided by I, the current which is supposed to go through that. Now, I is nothing but I is IAB by root 3. So, this is EL by IAB by root 3, which is into root 3. So, this is now this is nothing but R, the resistive component of the load. So, this is R root 3. Likewise, XC also the reactance, capacitive reactance is EL by I, which results in R root 3 value wise in ohms. So, this has a nice important implication. What it means is that, let us say we have a load R and you have a 3-phase system. We have a 3-phase system and we have just a single phase load R. This means that only currents will be flowing through 2 of the lines. One will be the forward path and one will be the return path, and the third line will not have any current flowing. So, it is an unbalanced system. In order to make the system balanced, meaning you have the same effective value of currents flowing through all the 3 lines displaced 120 degrees apart, you now add 2 reactances, one XL, that is the inductive reactance, and XC, the capacitive reactance, as shown, such that XL value will be equal to XL equal to XC equal to the resistive load into root 3. And if that is done, then automatically you will have the currents flowing here as this root 3 I and I, and they will be balanced when looked at from the point of view of the equivalent phasor diagrams, because equivalently if IBC is equal to I, ICA is equal to I, then what flows through this, what flows through this and what flows through this will all be equal. That is, it is equivalent to saying now that we have values here in this fashion. So, we have root 3 I, this is I and this is I. So, this is equivalent to saying that we have in this direction root 3 I by 2 is minus direction, that is this, plus ICA I cos 30, that is root 3 by 2 into I. And in this direction also we have the projection root 3 I by 2 is getting projected here and plus direction. So, that will get exactly cancelled out and you have just only the current in this direction. So, it will look and it would appear as though that the currents are balanced and equal in all the three phases, but the load is just only the active load is just only one value, which is R, if you take this condition. Is that clear? Probably we could consolidate it with some numbers now, numerical values. Let me take a simple, very quick numerical presentation so that you get the feel for it. So, let me take a textbook example. So, you have EAB, EBC, ECA all 120 degrees out of phase and they are 440 volts at a phase angle of 0 degrees, 440 volts at a phase angle of minus 120 degrees, 440 volts at a phase angle of minus 240 degrees. These are the EAB, EBC, ECA that will be applied. And the values of the resistance is can be calculated. Let us say we have a system which is being supplied by this and the single phase load that gets connected between is a 800 kilowatt load, let us say. So, then R would be 440 square by 800 kilowatts, which is 0.242 ohms. So, this is 0.242 ohms. And now, what should be the value of XL and XC? The value of XL and XC should be the value of XL and XC should be XL equals XC should be equal to R root 3 and that is 0.419 ohms. So, we put here 0.419 ohms, 0.419 ohms here also. One is capacitive, one is inductive. So, now if we look at the current through each of these. Now, the current through, let us say the reactance, the current through R, let us say IAB will be EAB by R, and that is equal to 1817 amps, isn't it? So, this is 440 volts at an angle of 0 divided by R, which is 0.242 will give you so much amps, that is 1817 angle 0 degrees is the amps. Now, if I want to find out IBC, so now IBC will be EBC divided by JXL, or which is equal to minus J EBC by XL, which is equal to, now EBC is 440 angle, we have angle minus 120. So, all these angles will get, there is a minus 90 provided by this J. So, this is going to be divided by 0.419 ohms. So, this would be 1047 amps at an angle of 210 amps. Then ICA is equal to ECA by minus JXC, which will be J ECA by XC, which is 440 angle minus 240 plus 90 divided by 0.419 ohms, and that would be 1047 at an angle of minus 150. Now, if these currents flow, then the projections of these currents, as we saw, these currents are now at something like this. These are the 1047 amps, and this is 1817 amps. So, there will be a projection on this axis that is negative, that will cancel out and give only the active power. There is a projection on this, and there is a projection along this, which will all tend to make it into a nice balanced load as we perform the calculation, so that this is equal to this is equal to this. So, there is one more small topic that we need to discuss, and that is just one moment. We go back here. We have calculated this. Now, what is IA, IB, IC, the line currents? IA, the effective value of IA, IB, IC, that is also to be calculated. This is IA, IB and IC. This is also to be calculated. IA is this current, that is IAB current, and minus ICA current. So, IAB current minus ICA current. So, this is equal to, this comes to around, let us say 1047 at a reference angle, let us say 0. Then one second. Then IAB. Now, let me just calculate the what happens. Oh, yeah. At a reference angle of minus 30 degrees, and IB. Now, IB is IBC minus IAB, IBC minus IAB, which is also 1047 at a reference angle of 210, and then IC is, if you look at this figure here, ICA minus IBC, ICA minus IBC, which is 1047 at a reference angle of 90 degrees. So, you will see that there is a phase difference of 120 degrees between the three phases of the line currents, and the line currents are balanced. However, you will see that in the case of the phase currents, we have this artificially included I and root 3 I, but effectively they all will cancel out if you put it along the 3 axes as we show along these, using these equations, which effectively cancels out on all the other axes, and you will have just only the IAB component which will flow through that, which is the effective power. But from the line side, from the source side, it will look as though they are balanced. Now, the new topic here is 3-phase power measurement. There are, I would say, 2 methods. One is to use oscilloscope with voltage probe and current probe, which would be the best method, because you would get the actual wave shapes of the voltage and the current waveforms, and you can probe the voltage and the current waveforms across each phase or across line to line, and once you get the line current and the line voltage, once you have line current and line voltage, and also the phase difference between the phi, which is the phase difference between the line and the current, looking at the wave shape of the voltages and the currents, you have root 3 EL IL cos phi. This is the power measurement. This would be one of the most accurate methods of obtaining the power. The other method is to use wattmeters. So, if we use wattmeters, the connections has to be done in the following manner. So, let us say we have the A, B and the C phase, which goes to the load. So, let us have the wattmeter like this, which and so we will call this the wattmeter, and the potential coil is between this, and likewise the potential coil is this. So, this is a wattmeter W1, this is a wattmeter W2. This is the potential coil connection, and this is current coil connection. Okay. So, the current of the A phase, current of the C phase is taken, the B phase is taken as the reference point, the potential of A phase with respect to B, C phase with respect to B is measured like that, and this of course goes to the 3-phase load, goes to the 3-phase load. Three-phase load. Now, on taking these measurements, the power P total is equal to the reading of W1 plus the reading of W2. This will give you the, this is called the 2 watt meter method. It is preferable to use a center 0 wattmeter, because if the power factor is less than 0.5, then one of the wattmeters can show a reading on the negative side, in which case you will have to take the absolute value and then add up for the total power to get the total apparent power which is fed to the load. So, if there is a center 0 wattmeter, then you can take the readings easily. Otherwise, if it is just only one direction wattmeter, you will have to reverse the direction if it goes negative, the power factor is pretty low. In the case of 3-phase circuits where the neutral is also available, meaning 3-phase 4-wire systems, then we just use, that is in case of a load which is 3-phase 4-wire, that is A, B, C and neutral, then with respect to the neutral we have wattmeters which are connected with respect to this, So, you will have W1, W2, W3. So, the P total would be W1 plus W2 plus W3 would be P total, the total power. This is especially useful when you are having a 3-phase 4-wire system. So, this is about the basic concepts of the 3-phase circuits, 3-phase systems we have been discussing about. They consist of essentially 3 sources, and 2 important constraints are applied for these 3 sources, and that is the amplitudes, the effective amplitudes of these three sources are equal, which means the peak amplitudes are also equal, and there is a phase shift in their waveforms, and each waveform is 120 degrees phase shifted with respect to the other. They are equally phase shifted with respect to the other. So, which means when you look at it in the spatial coordinates, so you will have three phasors which are in the form of a star and the form of a star equally spaced along the circle, which means 120 degrees with respect to each other. And then there are two major categories of three phase systems. One is called the star connection or star connected systems, and the other is the delta connection or the delta connected systems. In the star connected system, one end of the phase circuits of all the phase circuits are connected together, and that is called the neutral point. The other end of the phase circuits are brought out as terminals which can be connected to the source or any other load. The neutral points in the star circuits play an important role in the sense that if the loads are balanced, the neutral points can be left floating, because under balanced load condition IA plus IB plus IC is equal to 0, which we saw and discussed in the previous classes. So, therefore, there is no need to connect the central neutral point to the neutral point of the source. There need not be a return path wire. So, as a consequence, we save in copper in the sense that you just need 3 wires to connect from a 3-phase source to a 3-phase load. However, if the load is unbalanced, then IA plus IB plus IC is not equal to 0, as we saw, and therefore, we need to provide a path from a return path from the load side to the source side, and that return path is through the neutral wire, and under such conditions the neutral point of the load and the neutral point of the source are connected, and it becomes a 3-phase 4-wire system. Under unbalanced conditions, if such a neutral wire is not, neutral connection is not provided, then there will be distortions in the voltage wave shapes of the 3-phase circuits or the 3-phase loads. In the case of the delta, there is no concept of a neutral point. The 3-phase circuits are connected sequentially one after the other in the form of a ring, and the 3 phases are directly connected to the 3 points or the 3 vertices of a triangle are directly connected to the 3 points or the 3 terminals of the source. In the case of the delta, the line voltage and the phase voltages are the same, and in the case of the star, the line voltage is equal to √3 times the phase voltage. The line currents and the phase currents are the same. In the case of the delta, the line current is √3 times the phase currents. So, these are the 2 important relationships, voltage and the current relationships between the line side parameter and the phase side parameters of the 2 circuits. However, when it comes to power, the power equations with respect to the line side parameters is √3 EL IL cos phi, where phi is the phase angle difference between the line voltage and the current. If it is phase side parameters, then it is 3 times phase voltage into the phase current into the power factor or the cos of the phase angle between the phase voltage and the phase current. So, this is the power equations for both the star and the delta circuits. In the case of the delta circuit, we discussed one important unbalanced load condition, and that is, in the extremity, if we had just only one single resistor as a load. Then two of the lines will have currents in them, that is, one will have a forward current and one will have the return path current of the resistive load. The third line will not have any current and it will be just open. In order to balance the line currents, that is, the line currents should see the same amplitude effective values 120 degrees displaced with each other in the spatial coordinate system, the line currents. So, therefore, we do a modification in the delta circuit by including two reactive loads in the other two phases. So, we have a resistive load which is the active power which is going to be drawn from the mains. It is still going to be only the active power which is going to be drawn from the mains, but we add a capacitance and an inductance in the other two phases in a way such that if a value of current, effective value of current I is flowing through the reactive phases, that is the capacitance and the inductance reactive phases, root 3 times I will be flowing through the resistive phase, that is the actual resistance. Or in other words, if some load current is flowing through the resistance, load resistance, that current by root 3 should flow through the reactive components that we are going to put in the other two phases. This resistance, capacitance and the inductance will form a delta, and these phase currents will cancel out in such a manner that there will only be the current in the that will only result in the active component of the current. And on the line side, it will appear as though you have all three balanced currents flowing through it. Of course, one has to be careful in connecting these three components. One should not interchange the values, interchange the positions of these components, in which case you will have an unbalanced situation. And then we discussed about the measurement of power. The best method to measure the power in the three-phase circuit is by means of oscilloscope. You measure the voltage using a voltage probe and a current probe together. You measure the voltage in the current, line voltage and the line current, and then perform root 3 EL IL cos phi, and the phase difference can be obtained from the voltage and the current waveforms that can be seen on the oscilloscope. That would give you the best method. It is independent of whatever be the power factor. The other method is by using watt meters. One may use 2 watt meters in the case of 3-phase 3-wired system, that is neutral is not available. So, the 1 watt meter may be connected to one of the lines, and the other watt meter can be connected to the other line with the potential coils having the same third line as the reference. Then the watt meter values of the 2 watt meters are summed up to get the effective or the total power that is drawn from the source, or the total VA that is drawn from the source. Now, the total watts that is drawn from the source. In case the power factor is very low, in case less than 0.5, one of the watt meters can show a negative value, in which case we must reverse the if it is a single direction watt meter, we must reverse the switch such that you could see the negative direction power flow, or you use a center zero watt meter, in which case you take the negative value, convert it into absolute value, then add up the two powers. That would give you the effective, that would give you the equivalent total power that is drawn by the 3-phase load. If it is a 3-phase 4-wire system, then just connect 3 watt meters, add up the 3 values, you get the power. We stop here and then continue the next class with 3-phase transformers. Thank you.